We're here to talk about limiting reactants, and we're going to start out with a video clip here of some of our people from the stockroom doing what's normally a classroom demonstration. Okay, so I'll start this up and I'll set it up for you. Right now, in the flasks, you'll see the labels when they flip up the balloons. Each flask has hydrochloric acid in it. The solutions are all 2 molar HCl. There's different amounts. So on the left-hand side, there's 30 milliliters, then 62.5 in the middle, and then finally 90 milliliters of the acid. In the balloon, before they tipped it over there, in each of the 3 balloons, there was 1.5 grams of magnesium. So we're watching magnesium react with hydrochloric acid. When that happens, the magnesium will dissolve. It'll form hydrogen gas H2, and it'll form magnesium chloride, which is MgCl2. Okay, the hydrogen is a gas, and that's why the balloons are inflating. Okay, so as they react, you can see the balloons growing. The balloons are kind of bumping into each other, and a couple times over the course of this, they're going to separate the flasks a little bit, so they have a little bit more room, I think. And as it gets going here, you can see that the 2 balloons with the larger volumes, the 62.5 milliliters and the 90 milliliter balloon, those are both now bigger than the one that's on the flask with 30 milliliters of the acid in it. And we'll see as we get later on that they're about the same size as one another. Not much happens for a while here, so I'm going to roll myself forward in time to somewhere around here. So now in a moment, they're going to change views and let us see these from the side. And so you can see a couple things here. You can see that the balloon on the left, the one with the 30 milliliters of acid, is very definitely the smallest, right? That did not make as much hydrogen. The other 2 are at least roughly the same size. If this comes off perfectly, they are supposed to be the same size, I will confess. They don't always come out to be the same shape, for example, as they haven't here. Also, it's hard to see here a little bit, but if you look in the flask that had the 30 milliliters of acid in it, you can kind of see in the bottom that there's some of the magnesium flakes are still sitting there, right? There's a little bit of dark gray ring around the bottom of that flask. The one with the 90 milliliters of acid, if you look through there, that solution looks very clear. Okay, the one in the middle actually still has some bubbles going on because it takes a really long time for the last little bits of the magnesium to dissolve. Okay, in principle, what's happening here, this is the idea of limiting reactants. Okay, so in the one with 30 milliliters of acid, what happened is there just wasn't enough acid in there to dissolve all of that magnesium, and so there's some magnesium left over after the reaction stops. In the one on the far side, the 90 milliliter one, there was more than enough acid to dissolve all the magnesium. So all the magnesium is gone. If we tested the solution in that one, it would still be an acid because it would have extra hydrochloric acid still in there. The one in the middle, the reason why that's 62.5 milliliters and not just 60 milliliters, say, is because at 62.5, that one is supposed to be just the right number of moles so that the HCl and the magnesium are exactly enough to react with one another. And in principle, there shouldn't be any of either one left over in that case. Okay, so that's where there is no limiting reactant. I will tell you, we would say that for the small balloon over here, that's the case where the acid was the limiting reactant, and so there's magnesium left over. On the other end, the magnesium was the limiting reactant, so there's acid left over. And in the middle, we have the case where there's neither. We can't really tell that there's acid left over here just by looking in the flask, right? Because most of what's in the flask is water, after all. All right, that's one view of the limiting reactant. That's the sort of real life view. What would really happen if you were watching this in macroscopic space. Let's now take another look at this at a different point of view, okay? So the quantities we mix usually are not exactly what we would call the stoichiometric mixture, okay? So they don't run out at the same time. Just for your reference, that reaction we just saw would say magnesium, and the magnesium was originally a solid, so maybe I'll write that. Plus HCl, which was in aqueous solution. When that happens, we know we made hydrogen gas because we saw there was a gas. The only 2 gases we could possibly make here would be hydrogen and chlorine. Chlorine is quite toxic, and so we wouldn't be doing that just out in the open like that if that was what was being made. And the remaining product then has to have the magnesium and the chlorine in it. And so if we write that magnesium, if we look it up in the periodic table, is in group 2. That means it's Mg2+. Chlorine, we know, makes Cl minus because it's in group 17, and that means this thing needs a 2 on it, so it's MgCl2. So that would be my equation for this reaction. And then it's not balanced, so I have to hang a 2 on there, I guess, to make that all work, right? And then I have a balanced equation for my reaction for that, okay? And so that is the reaction that was going on in that video. So we talk about the limiting reagent is the one that runs out. Limiting reagent, limiting reactant. Reagent, reactant are synonyms. I probably say either one of those two terms each about 50% of the time. So just get used to thinking they're the same thing, okay? The limiting reactant is the one that there's less of, or there's not enough of to use up the other one. The one that there's plenty of is said to be in excess, okay? Usually if you're doing a reaction for any kind of practical purpose, you would choose what's going to be your limiting reagent based on some sort of practical considerations, often cost. If you're trying to make a product to sell it, and if one of your reactants is a lot more expensive or harder to get than the other, you would want to make sure that you got all of the expensive stuff made into product, right? If one of your reactants was water or oxygen that you could just get from air, you'd be willing to throw in extra air probably, because that would be the much easier thing to get, for example, than say whatever is your more costly reactant. Let's take a different look at things, okay? This is a molecular scale view of what it means to be the limiting reactant. This case, the reaction we're going to do is NO reacting with O2. So in this molecular cartoon, just like in the textbook, the red circles represent oxygen atoms, the blue ones represent nitrogen atoms. And so if I wanted to figure out what is the limiting reagent in this case, honestly, the best way to do this is probably just to sort of circle up sets that are two NOs and an O2. All right, so I might do, say, that clump there in the corner and say those can react together. I might take this one over here and say those can react together. Here's a set. There's nothing special about which groups I'm grabbing here. And here again are two NOs and an O2 that I can circle up. When I do that, I'll notice that what I have left over at the end is an oxygen molecule, okay? So that says I had more than enough O2, so my limiting reagent here looks like it was the NO, right? If I actually wanted to know what this thing would look like when it went to products, I could take each of my 4 circles there, and this says from each one of those circled sets of molecules, I should make 2 NO2s. So I should end up with 8 NO2s and an O2, which is a picture that looks like this one, right? Where, okay, my cartoon is not the best because I have all of my NO2 molecules like lined up pointing in the same direction, which would never happen in a real gas because they'd all just be sort of moving around and tumbling and what have you. But for purposes of counting, that shows us what we would get for products, right? The fact that there is a leftover oxygen up here tells me that there was at least a little bit excess oxygen. So I know the other one was the limiting reagent. Okay, so that's 2 ways of viewing this in more like physical level from the first example. This one is a little bit more, say, conceptual or molecular. The last way to look at this is just in terms of actually calculating things, right? Going to the formulas and equations version of things. So let's do that next. This is an example that involves limiting reagents, okay? We know that because it literally says so right on top of the screen. In actuality, the idea of having to identify that you're in a limiting reactant situation is one thing that often gives students trouble, okay? So I want you to get used to, when you read a problem, like stop and ask yourself, do I have to find the limiting reactant, okay, limiting reagent? The way to do that is, you know how I always say at the beginning of these problems, I say, well, start with the thing that you know. In this case, there's going to be more than one thing that we know. So we're going to have to do a step that lets us figure out which one we want to start from. Okay, so in this instance, what does it say? It says I have a reaction in which SiO2, that's silicon dioxide, loosely speaking, think sand, like beach sand, reacting with carbon, graphite, and chlorine gas to make silicon tetrachloride, SiCl4. The other product is carbon monoxide. Okay. That SiCl4 is actually of some value in the semiconductor industry. It's one of a number of ways that you can do things like lay down silicon on things and stuff like that. And so there is a bunch of this stuff made for industrial purposes because of that. The problem asks us how much SiCl4 could we make if we started off with 75 grams of each of the 3 reactants. So I have SiO2, carbon, and chlorine. These are my reactants over here, right? And my slide tells me that I have 75 grams of each of them. That's my problem. and I want to know, say, how many grams. I'm going to say how much. I should be more specific. I'll say how many grams of SiCl4 can I make. So that's my problem as summarized here, okay? How do I know if I don't have that writing on the top that says limiting reagent example? I know it's limiting reagent example because I know the quantity of all three of those reactants and I don't know which one I want to calculate from. Okay, so we have to learn a new beginning here, a step that comes before we do the actual stoichiometry problem. The first thing I want to do is still to take the things I know and turn them into moles. Okay, so let's do that first. I know I have 75 grams of SiO2. So if I take 75 grams and divide that by the molar mass, which for SiO2 is just about 60 grams per mole, I get 1.25 moles. Here I get 75 grams over 12 grams per mole. So I get 6.25 moles. And here I get 75 grams over 70.9 grams per mole. Again, you would probably you need to go and look up atomic weights to do that. I happen to have just written down the molar masses in the notes that I have next to me, which is why I just know all of those. 1.06 moles, okay? So now my job is out of those three numbers of moles to decide which one is the limiting reagent, okay? Now, you don't want to just rush to pick the smallest number of moles, okay? Because you also have to look at the coefficients in the equation, okay? And so if I look at these, the fact that I have three reactants here means I have to do a three-way comparison, right? Normally, if you only had two, then you can do it maybe a little bit more simply. In this case, if I look at these, you can do this in several different ways. One way is if you're comfortable with just looking at numbers and thinking about ratios, you can actually just think your way through it that way pretty easily, right? If I look at the carbon and the chlorine, for example, I need the same number of moles of them, right? Because they both have coefficients of 2 in the equation. I have a lot more moles of carbon than I do of Cl2. So that would tell me that I'll run out of Cl2 long before I run out of carbon. So I could relatively easily see that the carbon is not the limiting reagent, okay? So I might just cross that one out from that. Then I could look and I could say, I have more moles of SiO2 at 1.25, but I need more moles of chlorine, right? So in this case, I think it's relatively easy to see that the chlorine turns out to be the limiting reagent, right? If you don't like the idea of just saying, I can look at numbers and tell what it's going to be, and I know from experience a lot of students don't like that idea, here's a thing you can do that is a good way to systematically pick your limiting reagent. If you take those numbers of moles and you divide each of them by the coefficient on that substance, I'd have 1.25 and I would divide that by 1. Here I would have 6.25 and I would divide that by 2. I would have 1.06 and I would divide that by 2. Out of those numbers, if I pick the smallest one, that's the limiting reagent, okay? And so that says this one gives me my limiting reagent. Notice that when I write these, I didn't put that's that many moles, because this is how many moles of Cl2 we have, right? This number, when I divide that in half, one way to describe that is that's how many moles of reaction we can do. In the textbook, we have deliberately chosen not to use the phrase moles of reaction because it's very just confusing to a lot of people. But if you've, in an AP Chem class or something, have learned that idea, you can certainly call that moles of reaction because that's what it is, okay? So now, once I know what my limiting reagent is, my problem is simpler, okay? Getting this first step done takes us from having to find the limiting reagent to just having to do, whoops, I thought there was another slide there for me to write on, but apparently there's not. That means I'm going to need to give myself, no, I can do it down here. Okay. So that says I want to start from this one. Okay, because that's the limiting reagent. That's where I'm starting my stoichiometry calculation. Okay, so now I want to know how many grams of SiCl4 can I make from my 75 grams or 1.06 moles of Cl2. So I'm going to start with the 1.06 moles of Cl2. The reason I'm going to start there is because if I start with the 75 grams, the very first thing I'm going to do is turn it into moles. I've already done that, so there's no reason to go back to that step. Then I get a mole ratio which says 2 moles of Cl2 make 1 mole of SiCl4. And then I get a step that says 1 mole of SiCl4 is equal to about 169.9 grams. And my notes say that gets me about 85.4 grams of my, my SiCl4 product. Notice, very important thing, when I did this, I started my calculation with 1.06 moles. That's the actual number of moles of Cl2. I did not start here by saying I had 0.53, right? Because I don't have 0.53 moles of Cl2. If I start off with this 0.53 and I put this 2 down here again, then I will have divided by that same 2 twice, and I'll get the problem wrong, okay? So be very careful about that. I see students do that a lot. If you're going to want to start from this number, you have to be clever enough to realize that means you already divided by this 2. Okay, I recommend going back to the actual number of moles, because then this step down here is just our sort of base level stoichiometry problem, the one that we talked about in video from the other day. And that says, once I do the limiting reagent step, I say, okay, now I'm in a problem that I already learned how to do, and I can take it from there. All right, we have one more idea to introduce in this, video, just because it doesn't take too much time, doesn't merit a video of its own, and that's the idea of reaction yields, okay? In real life, when we do a chemical reaction, we almost always end up with less product than we would expect. Okay, there's a variety of reasons for that. Okay, students often say, well, I just messed up, I didn't do it right, or something like that. That's not entirely the only reason. Okay, that could be a reason. If I spilled some of the reactants on the floor or on the benchtop in the lab, then yeah, I'm going to get less product if I didn't actually put all the reactants in there, right? But it could also be that the molecules, when you mix them together, you had written down one reaction and said, this is what I'm trying to do, but maybe the molecules had some other reaction that they could also do, and they made some other products that were not what you were trying to make. Okay, that's the idea of competing reactions, where you can't control what exactly what reaction is going to happen, or you can't always control it. It could be that your one or more of your reactants had some impurities in it. It wasn't really 100% the stuff you thought it was. It could be time, right? Like, gosh, when I stopped the video there, I pointed out that there was still a little bit of bubbling going on in the one solution in the middle, which meant some reaction was still happening. So if you weigh your product or measure your amount of product before the reaction is finished, you won't have as much. Okay, so these are often described in terms of a percent yield. That's just kind of like, how does what you actually got compare to what you hypothetically thought you should get? So the calculation for this is really easy. Okay, the percent yield is the actual yield divided by the theoretical yield, just multiplied by 100%. The actual yield is what you really got. That requires that you actually have done an experiment to get that yield, right? So you actually have to do the thing, separate out the product, say weigh it or whatever, somehow figure out how much of it you've got, and that's your data. The theoretical yield is what you expected to get. That one you would find by doing a stoichiometry calculation, right? You'd say, I had this much of this reactant, this much of the other reactant. I expected to get X amount of product, okay? In almost all cases, the actual yield will be at least somewhat less than the theoretical yield. There are some exceptions to that. If you do a reaction where, gosh, a reaction's taking place in solution and maybe it makes a solid product and you're trying to weigh that solid product, particularly if you're in some of our teaching labs, oftentimes students will be in a hurry to leave and they won't wait long enough to get that product really dry. In that case, part of the weight when you weigh it is actually water, and sometimes then you might end up with the product seeming like it's heavier than it's allowed to be. That's usually just because there's something in your product that's not what you think it is. Okay. In general, that actual yield is going to be less than the theoretical yield. Students often ask, if I had a room full of you in front of me right now, it's a pretty fair bet somebody would ask, well, how big is a good yield? Like, what percentage should it be? The answer to that really depends heavily on how important the thing you're trying to make is. Right. So if you were in the I don't know, pharmaceutical industry and you were working on designing a synthesis path to make some super drug that was going to be useful in cancer treatment or that was going to be useful in treatment for COVID patients right now or something like that, you'd be thinking like, well, this stuff is worth a lot if we make it, and so even if the yield is low, we'll still have the stuff and people want it, and I should do that, right? If, on the other hand, you could raise that yield up, then you could obviously get, you'd have more of the stuff to sell and your business would make more money, okay? One complicating factor is that a lot of practical reaction pathways don't just have one reaction. They might have, 5 or 8 or 10 steps in them. And if you have 10 steps in there, if the percentage yield of all your steps anything other than quite large, by the time you multiply all those percentage yields together, you're not getting a lot of product, right? And so it is often important to boost up these yields. A lot of people in chemical engineering that work in production plants and whatnot, this is a lot of what they try to do, is find ways to improve those yields, because that just means you're getting more sellable product per input of reactant, and that leads to better profits, right? So that's a thing that a lot of people work on really hard. Right, a quick example just to illustrate this. So what have I got? I've got a very simple reaction here, just a combination reaction really, NO and NO2, making N2O3. I just chose a nice simple thing. It says 10 grams of NO react with 14 grams of NO2 to produce 8.52 grams of N2O3, and we want to know our percentage yield. Okay, so let's see what happens here. I guess I gave myself a slide for this one and not for the other one, which is weird because I probably didn't need it here. But so the first thing I'm going to do is look at this, and I'm going to say I know the masses of both things that are reacting, right? So particularly because we're in the video where that's the title of it, and we just did the other example, hopefully you have bells going off in your head right now saying it's a limiting reactant problem, okay? Because I don't know which of those two masses I want to start from to figure out how much product I should get. Okay. Some of you are also right now quite concerned because that says I mixed together 24 grams of stuff and made 8.5 grams of stuff, right? That's clear evidence that there's something else being formed besides what we're looking at, right? So there must be some other product, some other reaction happening, presumably, that lets us do that, because we've obviously ended up with a lot less stuff than it says we started off with. Because it's a limiting reactant problem, my first step is to turn both of those masses into moles, okay? So this one is 10 grams divided by 30 grams per mole. So that's 0.33 moles. This one is 14 grams divided by 46 grams per mole. So that's pretty close. That's 0.304 moles. My equation is 1-to-1, right? And so because of that, I can just say the one that has fewer moles here is very definitely the limiting reactant, okay? Because I need the same number of them, right? So the one that I have less of is this one. That's my limiting reactant. So that says from my 0.304 moles of NO2, I should have expected to make 0.304 moles of N2O3, right? So let's just do that as a formal stoichiometry calculation. 0.304 moles of NO2. 1 mole of NO2 makes 1 mole of N2O3. And again, I probably wouldn't in normal circumstances, and a lot of you might not bother to actually write out a step like that because it's pretty obvious looking at it that it's just like 1-to-1. My next step says moles of N2O3, and I need a mass. Notes over there say that's 76 grams. And so if I multiply that out, that's 23.1 grams of N2O3. And so then I want to just find my percent yield, because that was my question. I actually made 8.52 grams, so that's my actual yield. I divide that by my theoretical yield, which is that 23.1 grams we just found. I multiply by 100%. So I get a percentage rather than a fraction. And my notes tell me I get 36.8% for my yield, okay? So about that mass that's gone missing, a little bit of it is NO, according to this, right? Even if nothing else had happened to react, I'd have some NO over there, but it's obvious that I didn't make all the NO2 into N2O3 either. So in this case, nitrogen and oxygen could form a lot of different compounds, and so I must have some other things that have been formed that are just not accounted for in my equation, okay? To be honest, I literally just made up those numbers, and so I have no thing in mind for what the rest of it is. I just picked numbers at random to make the problem so we could calculate it. All right, but that's another example of limiting reactant, in this case without the big banner headline saying limiting reactant problem. So if you recognize that as having to do that first, then that's a good early sign. And then it just shows you that the calculation for the percent yield is a relatively simple one, nothing to really get excited about there.